Okay, so in the last video, we talked about the quantum model of an atom and all of the possible energy levels and sublevels and orbitals in that in an atom, and how many electrons can fill each, etc. So in this particular tutorial, we are going to actually start talking about electron configuration. So first we'll cover what that actually is. We'll explain what it is. And then I will go into a discussion of how electrons will fill the orbitals of an atom. And then third, I will actually show you how to do an atom's or an element's electron configuration. So electron configuration is just a way of describing where the electrons of a particular atom are located. And when we say where they're located, it's kind of like an address. So you're telling what energy levels and the orbitals or sublevels that you're finding each electron of that atom in. And the other piece of information that you can get from an electron configuration is a description of the order in which the electrons actually filled the atom. And that'll make more sense here in a second. So let's look at nitrogen. Nitrogen is an atom that contains 7 electrons. And an electron configuration for nitrogen will tell me where or what energy levels and sublevels or orbitals I will find each of those 7 electrons. And the electron configuration for nitrogen looks like this: 1s2, 2s2, and 2p3. So the way that you read this is the 1 right here means that in the first energy level of nitrogen, in the s sublevel, or in an s orbital, you will find 2 electrons. So 2 of nitrogen's 7 electrons are located in the first energy level in an s orbital. Okay, and then the second part here, the 2 means that in the second energy level of a nitrogen atom in an s orbital, right? So there's the s right there. You will find 2 more of its electrons. So we've just told you where you can find 4 of nitrogen's 7 electrons. And then the last part tells us that in the second energy level, in a p orbital, you will find 3 electrons. So we have told you the location of all 7 of nitrogen's electrons from this electron configuration. Okay, so let's talk about the order in which electrons fill the orbitals of an atom. So when electrons fill the available orbitals of an atom, they do it in a particular order, and they do it in the order of lowest to highest energy. So electrons will actually start to occupy the lowest energy electron orbitals first, and then they'll go to the next highest energy, and then the next highest, and the next highest. So they will never fill high level or higher energy orbitals if there are lower energy orbitals empty. All right, so there is an order to this, and it doesn't just go in numerical order necessarily. So we've got a little image here that sort of shows you the order that they fill. So the arrows right here show you that the electrons will fill the 1s orbital, and then once that's filled, they'll fill the 2s orbital, and then once that is filled up, they'll fill the 2p, and then the 3s, and then the 3p fills up, and then the 4s, and then the 3d, and the 4p, and then the 5s. And so you get the idea that this is the order in which the energies of the orbitals go, and the order in which the electrons will fill an atom. Now, this picture over here, right here, shows you exactly the same thing, but it just kind of shows it in a little more detail. So, for example, gallium. Gallium has 31 electrons. And when those electrons fill a gallium atom, they fill them in a particular order, in the order that I just showed you. So remember that each orbital can only hold or each, yeah, it can only hold 2 electrons. And hopefully you remember that when you draw the electrons in an orbital, you draw them as arrows, one up and one down. So gallium, if it has 31 electrons, is 2 of them will go in the 1s orbital first. So we'll have 1s2. And then 2 of them will go in the 2s orbital, so 2s2. So that gets us to 4 electrons. Then the next orbital that fills is going to be the 3p orbitals in our 2p sublevel. So you'll get 2 electrons here, here, and here. So that gives us 2p6. And then you've got, 2 more electrons will go into the 3s sublevel. And then our 3p sublevel will end up with 6 electrons total, 2 in each of the p orbitals, so 3p6. And then the 4s fills next, so 4s2. And then notice that the 3d has a less energy than the 4p. So the 3d electrons will fill up next. So you'll get 2 in each orbital. Sorry, it's kind of messy. So that's 3d10. And then that leaves us with 1 more electron because we're trying to get 31. And that 1 electron will go into one of the 4p, the first of the 4p orbitals, so 4p1. And you get a total if you add up the electrons here, 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 like all of these, you should get a total of 31 electrons. So this is how the orbitals would fill for any atom, and this is what specifically gallium's orbitals or orbital notation would look like. Okay, so there are a couple of rules that you need to know about electrons and how they fill these orbitals. All right, so the first rule we've actually already talked about, which is called the Aufbau principle. The Aufbau principle states that electrons will fill the lowest energy available orbitals first. So when an atom's electrons are filling its orbitals, remember each orbital is going to get 2 electrons. So if an atom has, say, 6 electrons, making that a carbon, right? 2 of its electrons will go in the first energy level in the s orbital first, and then 2 in the 2s orbital. And then you will get electrons filling the p orbital. So it's not like you would get, so that's correct, right? It's not like those electrons would just go wherever they feel like it. So you wouldn't get them going into the 3s before the 2p, because the 2p is at a lower energy level or a lower amount of energy. So that would be incorrect. They would have to fill the p orbitals before moving to the s. Okay, the second rule is called Hund's rule. And Hund's rule says that electrons must fill the orbitals that have the same energy or are in the same sublevel one at a time. So let's talk about carbon again. So carbon has 6 electrons. So in its first energy level, it has 1 orbital, an s orbital. And so 2 of those electrons will go in that s orbital. And then 2 more of its electrons will go into the 2s orbital. Now here's where it gets tricky. That gives us 4 electrons and there are 2 left. Now it's tempting to, in your p orbitals, just to go ahead and shove 2 electrons into one of those 3 p orbitals. But the fact of the matter is that those p orbitals are contain or have the same amount of energy. And so what that means, according to Hund's rule, is that if orbitals have the same energy or are in the same sublevel, that electrons are going to spread out. So think of it like this. Electrons don't like each other, and if they have 3 available orbitals in the same sublevel, they're going to spread out. They're not going to occupy the same orbital if they don't have to, because electrons are negatively charged and they're repelled by each other. So Hund's rule states that if you have 3 orbitals, like these 3p orbitals, that are all the same energy that the electrons are going to fill them up one at a time before they start doubling up. So let's look at what something like nickel would do. So remember that if the orbitals, if a sublevel has more than one orbital in it, those orbitals have the same amount of energy, and so electrons will fill them one at a time. So let's count it out. Nickel has 28 electrons. So we know that 2 of those electrons will go in the 1s orbital, and then next the 2s. So that's 4 electrons so far. And then as far as the 2p, the way that it would fill is you would get, so we had 2, 4, 5, 6, 7, and then they would go in and double up 8, 9, 10, and then 11 and 12, 13, 14, 15, 16, 17, 18, 19, 20. Now notice the 4p is above the 3d, so we're going to go into the 3d sublevel. 21, 22, 23, 24, 25. Now they'll double up 26, 27, 28. So that leaves 2 orbitals in the 3d sublevel half filled, which is fine because those electrons aren't going to want to try to cram into an orbital when they don't have to. So that's Hund's rule. All right, the last rule to orbital filling is that any electrons occupying the same orbital must have opposite spins. So what I mean by that is that, you know how I've been drawing one arrow up and one arrow down within an orbital? You never see it like 2 arrows up or 2 arrows down, like that's not correct. This really gets down to kind of a quantum thing where electrons have spins. So if here's an electron, it actually has a spin on its axis, and so it can spin either clockwise or counterclockwise. And Pauli basically said that electrons that are occupying the same orbital have to spin in opposite directions. And there's a reason for it that you don't need to know. You just need to make sure that when you're drawing electrons as arrows in orbitals, that you always put one up and one down. So if we were doing the electron configuration for carbon, or rather the orbital notation for carbon, which has 6 electrons, you would put 2 here, 2 here, and notice in each orbital you've got one up arrow and one down arrow. And you would have, say, 2 here. And I want you to notice that you never ever see like this, 2 down or 2 up. That would be incorrect. So that's the Pauli exclusion principle. So how do you actually do electron configuration and ensure that you have the right number of electrons in each orbital and that you have the orbitals in energy from low to high? The easiest way is to use your periodic table for help. So I have the electron configuration for nitrogen up here already, and I'm going to show you how I actually got that electron configuration right now. All right, so we're going to mark our periodic table up. So these first 2 columns on your periodic table I've circled in blue. I want you to circle those or outline them in a color and mark them S above them. And then I want you to pretend like helium is right there. Even though it's not, we're just going to pretend that it is for now. Okay. And so we've marked up something called the S block. And in the middle, this block in the middle that I'm outlining in purple, I want you to label that the D block. And in parentheses next to it, I want you to put n-1. That will make sense in a minute. And something that I'm noticing while I'm at it, see this little square that says 57 minus 71? I want you to put, on your periodic table, I just want you to notice that lanthanum is written in there. And same with the one beneath it. AC is written in the one beneath it. And I want you to cross them out from here and here. All right. And then over here, this block right here, not including helium because we moved helium. This is your P block. And then at the bottom, you have this other block at the bottom. And I want you to label that the F block, or just F, and then put N-2 in parentheses. And this will all make sense here in a moment. So essentially what we're doing is we're using the periodic table to count out electron configuration. So if I were to ask you to do the electron configuration for, say, nitrogen, so here's nitrogen on your periodic table. You're counting through rows and through blocks to get to nitrogen. And something else I wanted you to notice is that along the side of your periodic table, you have these numbers that number the rows. And there are 7 of them, so 7 rows. All right, so let's do the electron configuration for nitrogen. So you already know what it is, but I'm going to show you how I got it. So we are trying to get to nitrogen, which is 7 elements into your periodic table. And so to do electron configuration, you always start at the first row, and then you just count the row, the block, and then how many squares there are. So again, we have to count through all the squares to get to nitrogen. So in the 1s row, there are 2 squares. And then there's nothing for the rest of the periodic table, remember, because we moved helium over to the s row, or s block. And then we'll drop down to the second row, and we'll count over 2 elements in the s block, right? So it's an s block, 2 elements. So that puts us right here. We need to get over to nitrogen. Now, remember, nitrogen's still in the second row. So we're still in the second row, but now we're in the P block, and we are 1, 2, 3 elements over. And that's how we got the electron configuration for nitrogen. So let's try sodium. Sodium has 11 electrons. So we're going to need to account for all 11 electrons. So we'll do sodium right now in green. So there's sodium. Sodium's in row 3 in column 1 in the S block. And we need to count through every box until we get there. So we start again at the first row, and we're in the S block, and we count over however many boxes there are, and there are 2. Remember, again, we moved helium. And then we drop down to the second row, and we're still in the S block, and we count over 2 elements, or 2 boxes. And then we continue, we're still in the second row, but now we're in the P block, and we count 1, 2, 3, 4, 5, 6 boxes. And then we drop down to the third row, and we're back in the S block, and we're over to get to sodium, 1 box. So there's sodium's electron configuration. And if you remember correctly, the electrons have to add up to 11, right? Because it's sodium. So if you have 2 plus 2 plus 6 plus 1, that adds up to 11 electrons. And this shows you the electron configuration for sodium. So let's do something a little bit harder. Let's try iron. Iron has 26 electrons. So first, let's find iron on your periodic table. And iron is right here on your periodic table. It's number 26. So that means we have to count through 26 boxes to get to iron. So where do we start? We always start at the 1, or at the first row. So 1, and again, we're in the S block, and we count over 2 boxes. So 1s2. And, remember, we moved helium. And the second row, we're still in the S block, and we count over 2 boxes. And then we follow this over. We're still in the second row, and we're in the P block now, and we count 1, 2, 3, 4, 5, 6 boxes. So remember, we're trying to get to iron. We're not there yet. And then we go down to the third row, and we're in the S block again, and we count over 2 boxes. And then we follow that over, still in the 3rd row, but now we're in the P block, and we count over 1, 2, 3, 4, 5, 6 boxes. Okay, so now we drop down to the 4th row. And we're in the S block again, and we count over 2 boxes. So now here's where it gets a little bit confusing. So this you're gonna have to mark this up on your periodic table as well. When you get to this D block in the middle, remember I told you that D is n minus 1. So what that means is that when you get to the D block, the rows are numbered 1 back from the row that you're in. So n minus 1 means 4 minus 1, or 5 minus 1, or 6 minus 1, or 7 minus 1. So once you get to the D block, this becomes 3D instead of 4D, and then 4D, and then this is 5D, and this is 6D. Those are kind of hard to see, but just remember that the D block is always backed up 1 from whatever row, right? You're in row 4. So whatever row you're in, you back it up or you subtract 1 from that row, only when you're in the D block. And then once you get back over to the P over here, this goes back to being 4P, 5P, 6P, and 7P. So if we are continuing our electron configuration, we got through 4, so 4S, 1, 2, and then we go 3D, because we're in the D block, 1, 2, 3, 4, 5, 6. So 3D, 6. Okay, let's do yet another one. Let's go ahead and do indium. Now remember, I'm going to go ahead and mark it up again. Remember when you got to the D block, this was 3D, this was 4D, 5D, and 6D. So don't forget that the D block is n minus 1. We're trying to get to indium. Indium's right here. It's number 49 on your periodic table. So let's do indium. All right, so we start at the first row, S block 2. So 1s2. You're going to start to realize that you repeat a lot. You'll get used to that. And second row, S block 2, 1, 2. And then, okay, and we're still in the second row. Remember, you follow it over. And you're in the P block now. And you count 1, 2, 3, 4, 5, 6, so 2P6. And then go down to the third row. We're back in the S block. So 3S, and then count 2 over. And then follow the row, and you're still in the third row, but now you're in the P block. And you count the boxes, and you count 6 over. Now we're down in the fourth row, back in the S block, 2. And then, remember when you get to the D block, you have to subtract 1 from whatever row you're in. So we're in 3D, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 over. And then once you get back to the P, you're back in the fourth row, 4P, and then 6, 1, 2, 3, 4, 5, 6. Down to the fifth row, you're in the S block, and you'll count 2 over. And then you're in 4D now, because you're in the D block. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then you're back in the 5P block, and you're 1 over at indium. Now, when you get this far in, I like to make sure that my electrons add up to the number they're supposed to. So they're supposed to add up to 49. So 2 plus 2 is 4. Plus 6 is 10, plus 2 is 12, plus 6 is 18, plus 2 is 20, plus 10 is 30, plus 6 is 36, plus 2 is 38, plus 10 is 48, plus 1 is 49. So it indeed adds up to 49. So before I end this video, I wanted to just show you one last thing, and that is the F block at the bottom. So remember with our P block, how when we got to, with our D block, when we got to the D block, we subtracted 1 from whatever row you were in. So even though we're in the fourth row here, we called this row 3D instead of 4D because we subtracted 1 from n, which is the principal quantum number. And then when we were in the fifth row, when we got to the D block, we called this 4D. And then when we were in the sixth row, we called it 5D. And then when we were in the seventh row, we called it 6D. Well, the same is true when you're down in the F block. So the F block has the same rule, only it's n minus 2. And something that's maybe something that you didn't notice already, the F block actually fits into here. So this little block right here actually fits in between barium and hafnium, or radium and rutherfordium. That little chunk should just go in this little space. And so that can be a little bit weird, especially when you're doing electron configuration for things that are like over here or things that are down in here. So you have to remember that that little chunk kind of fits in there. And since it is an F block and it's n minus 2, then we call this first row, if that first row actually fits right in here, we call this first row, so we're row 6, right? This first row right here, if it's n minus 2, is 4f, because 6 minus 2 is 4. And then if this row below it fits into the seventh row, 7 minus 2 is 5, so that's 5f. So when you might want to mark those, 4f and 5f. And then the same thing holds true. When you get to those rows, you plug those rows in before you get to the D, and then you count through the D. So let's do one really fast. Let's do lead. Lead seems like a good choice. So let's go ahead and do lead. Okay, so lead has, I just crossed it out, 82 electrons. I'm kind of going to go through this really quickly because this video is getting lengthy. So follow along with me. We'll do this in green. Okay, so first row, S block, 2 over, 1s2. Second row, S block, 2 over, 2s2. And then we're still in the second row. Now we're in the P block, 1, 2, 3, 4, 5, 6. Okay, third row, S block, 2 over. Still in the third row, P block, 6 over. Go to the fourth row, S block, 2 over. And then remember 3D. So we had 2 over, 3D will go 10. And then that puts us back in the 4P block over here for 6, 5, S block, 2. And then 4D, 10. And then 5P puts us right here, 6 over. Okay, so this is where it gets a little tricky. So now we're in the sixth row. We're in the S block. And we count over 2. 1, 2. Now, lanthanium actually is number 57. So remember down here how I crossed lanthanium and actinium out? So we're going to start with cerium, because cerium in this whole entire row plugs in right here. So that puts us at 4F, and there are 14 elements in the F rows. So 4F, 14. Then we're in 5D because now we have to count where lanthanium through mercury are. So 5D, and there are 10 of those elements. 10. And then we're back in the sixth row, 6P2, to get you to lead. All right, so that is kind of electron configuration in a nutshell. I know it was lengthy, but you guys are going to be fine.